Okay, here we go. All right. Um, all right, so let's do kind of the sort of our big picture now so we can see sort of where we're going. All right, so we've been looking at enthalpy and hang on a second, let me just make sure it's my, yeah, okay. All right, so we've been looking at enthalpy, and so far we have looked at calorimetry, which that's our what I would call our experimental way of finding enthalpy, right? Because we use Q equals MC delta T, and then we use that delta H is, well, Q per mole, okay? So now what we want to do, all right, is we're going to look at other ways that we can find enthalpy. And the key reason that we can use these other methods is because enthalpy is a state function, meaning that its value, it only matters where it starts and where it ends. And so if it takes 2 steps to get from the start to the end, or if it takes 5 steps to get from the start to the end, the enthalpy value will still be the same. All right, so that's kind of why we can use these other methods. So we're gonna focus today on a method called Hess's Law, all right? But then we'll also use our heats of formation, and then at the beginning of next semester, we're gonna look at finding enthalpy based on bond energies, okay? So these 2 will be in this unit, and then bond energies will come next semester. Okay, so with Hess's law, what we do is we take advantage of the fact that there are a lot of reactions for which the delta H is known. And if we can combine those reactions in a way that when we put them all together, they give us the reaction we're interested in, that the delta H I get by adding up all the enthalpies of the reactions I'm combining will be the same as the delta H for the reaction that I'm wanting to know about. All right, so oh my goodness. Okay, so let's take a look. We got some rules that we're going to work with here. So I'm going to go to a different page to do these rules. Okay, so when we're talking about delta H's for a reaction, all right, so the delta H for the forward reaction, that means like as it's written, reactants to products, is equal to the negative delta H for the reverse. So that means if I flip a reaction so that the products now become the reactants now become the products, that the delta H, the magnitude of the value stays the same, but the sign changes. Okay. And which that sort of makes sense. If you think about it, if I'm doing, like, let's do something really simple. So, like, if I am, say, if I'm melting a substance, okay, right, we know that takes energy in, so it's gonna have a positive, hang on. Okay, sorry about that. Alright, so then if we just flip it, so we go right where we are then freezing, right? We are removing the same amount of heat if it's the same amount of water, so it's gonna have same value, just negative on there. Alright, so flipping it changes the sign. Then the other thing is that if I, uh, multiply a reaction. Alright, so let's just make up a reaction. Alright, let's make it a single replacement reaction. Alright, so if that has a certain value for its delta H, okay, if I multiply through that reaction, so say I'm gonna multiply everything in the reaction by some value n, then it also multiplies the delta H by that factor. Okay, it changes by the same amount. All right, so we've got, so this is our one thing we're going to use there. And then we're also going to be using, okay, so these are two ways that we can manipulate the equations and what the subsequent effect would be on the delta H value. All right, so now let's look at what happens when we are going to add a bunch of equations together. Okay, so if we are adding equations, and this is gonna make a lot more sense once we actually start doing some problems with it. If I'm adding equations, if I have the same substance on the same side, then we add those together, all right? And same side means, like, they're both on the reactant side of more than one equation. If I have the same substance on opposite sides, they cancel each other out. Okay, meaning if I have the same thing on the reactant side and the product side, then those will cancel each other out. Okay, so those are the 4 rules that we're gonna use. Alright, now I'm gonna go back to, we're gonna use some problems from the textbook. Okay, and now these, and actually, where did let me, what I'm gonna wanna do, alright, and what you're gonna wanna do with these is we're gonna wanna rewrite them and put some space in between them, okay? Alright, so NH3, let me just make sure. On these, okay, I don't have anything that is like the same substance in a different state, okay? So I'm not gonna copy the states, but if you have an equation, like one equation where you maybe have water as a liquid and another where you have water as a gas, those don't cancel each other. So when I say they're like the exact same thing, they have to be, the formula has to be the same and they have to be in the same state also. But here, I don't have that issue, so I'm just gonna look at, alright, 1/2 N2 plus 3/2 H2, and that, I'm gonna make a column here from the delta H. The delta H of that is 46 kilojoules. Okay, so then I have 2H2 plus O2. Skylar, shh. is 2H2O, and that is minus 484. Okay, and then now the equation I'm wanting to find the delta H for is this 2N2 plus 6H2O gives me 3O2 plus 4NH3. Okay, so what I want to do is I want to manipulate the two equations that I know what their delta H is, so that when I add them together, it gives me the equation that I'm wanting to find the delta H for, because then I can just add the delta H's for each of those equations, and that will give me the delta H for my unknown equation. Okay, so let's see. I want to, all right, so well, the easiest way to start this is to look for, um, start with things that are only in one of the given equations. So here, uh, let's start with the water. All right. So water, it's only in this equation. Now I need it on the reactant side because it's on the reactant side here. So I'm going to flip this equation. All right. So I'm gonna flip it. So 2H2O is 2H2 plus O2. And when I do that, it changes the sign on my delta H. So I'm going to mark through the equation that I started because I'm not using it anymore. Now I need a, so the water's on the right side, but now I need a 6 on it. So I'm going to multiply through everything by 3. So that'll give me 6H2O yield 6H2 plus 3O2. And then what that's going to do is it's going to multiply the delta H by 3. So I'm going to mark that one out. Now, what I usually do is once something is on the correct side and it's got the coefficient that I need it to have, I'll put a box around it just to let me know that it's okay and that I probably don't want to mess with that equation anymore. All right. So not only do I have the water where I need it, that also fixed my oxygen. So now we need to manipulate top equation. All right. And I need a 2 into, needs to be on the reactant side. So I'm going to flip this. Okay. Let's stick with a different color here. All right. So I get 3 halves H2 yields. Oh, nope. Wait a minute. Let's try that again. Plus 1 half plus 1 half into, and that's going to give me NH3. So that's going to change the sign. So that's going to make that a minus 46. And then now it needs to be a 2, and it's starting with 1 half. So I'm going to multiply everything by 4. So 12, let's see, 12 halves, that's going to give me 6 H2 plus, and then 4 times a half will give me 2 N2 and 4 NH3. So that's going to give me 4 times 46. Mark through that. So the N2, that's okay, and NH3. All right, so I have the 4 things that I need, and then but I need to make sure does my H2 cancel. I have 6 H2 on the reactant side and 6 H2 on the product side, so those are gonna cancel each other out. So now the only thing left when I add these together, if I add that to that, I get 6H2O plus 2N2 yields 4NH3 plus 3O2. And so if the equations add together, then I can add their delta H's. So my delta H is gonna be negative 4 times 46 plus, so that's this one, and then this one here, plus 3 times 484 on there. So it's kinda like doing a puzzle, sort of. So -4 times 46 plus 3 times 484, and that gives me a positive 1,268 for the delta H for this reaction right here for mine. Okay. Alright. So let's look at another one here. Alright. Okay, I'm gonna pull this off to another page here. Let me grab this one. There. Okay, and then go back to this. Okay, and again, I'm gonna just rewrite these just to spread them out a little bit. So 2ClF plus O2 Cl2O, F2O. My delta H is get 167.4, and then 2ClF3 is 2O2 Cl2O plus 3, and that's 341.4, and then 2F2, let me make this bigger, there, plus O2, 2F2O minus 43.4. All right, we're trying to get ClF plus F2 is ClF3. All right. Okay, so let's see. All right, ClF is only in the first equation. So let's start with that one. And here I need a 1. It's got a 2, so I'm gonna multiply through by 1/2. So that's gonna make a little note over here, times a half. So that's gonna be ClF plus 1/2 O2 and 1/2 Cl2O and 1/2 F2O, and my delta H is 167.4 times 1/2. Let's mark through that. Okay, so this one is where I need it to be. Okay, now I need just F2, and it's only in the bottom equation. So I'm gonna do the same thing, I'm multiply by half. So that gets me F2 and 1/2 O2 and then F2O. So I'm gonna take that times 1/2, mark through that. Okay, so this is now where I need it to be. Alright, and the ClF3, okay, it's here. Let me change colors. This is getting mixed up here. Oops, where did it go? Oh, sorry. There it is. Okay, so here I need, oh no, it's on. Okay, it's in 2 places. One, oh, it's in all 3. Alright, let's see. So I need it to be, okay, so I'm gonna flip it and then multiply through by 1/2. Okay, so, and let's just do that all at once. So I'm gonna flip and times 1/2. So that'll give me 3 halves F2O plus 1 half Cl2O gives me ClF3 plus O2, and so that's gonna give me a minus for the flipping, and then times 1/2. So let's mark through that. Okay, so the ClF3, that's where that needs to be. So now we need to see if everything else is canceling. Alright, so what do I got? On for the O2s, I have a 1/2 and a 1/2 on the reactant side, and then I have a 1 on here. So these 2 on the reactant side cancel that 1 on the product side, and the Cl2O, I have a 1/2 and a 1/2, so that cancels, and then I have a 1 and a 1/2 of the F2O product side, and then I have 3/2 on the other, so that 3/2 cancel the 1 and the 1/2. So everything I don't need cancels out. Okay, now my delta H then for this equation is going to be 167.4 times 1/2, uh, plus a negative 341.4 times 1/2 plus a negative 43.4 times 1. Alright, so that gets me 167, 2 plus a negative 341.4 plus a negative 43.4. Okay, so I'm getting a negative 108.9 for my delta H for that one. Okay. Um, alright, let's okay, so let's go to 62 here. Okay, and let's move it to another page. Okay, leave that equation up there. It's the one that I want. Let's see what we got here. C6H4OH2 to C6H4O2 plus H2. Oops, let me move that down a little bit. Okay, H2 plus O2, H2O2, and I get a minus 131.2 H. Okay, let me make sure here. Do we have yeah, the water. Okay, so the water in this one, we've got to pay attention to the state because I've got it one equation as a gas and the other as a liquid. Okay, so this one, H2 plus 1/2 O2, that gives me H2O gas is 241.8. Okay, and then H2 H2O gas to H2O liquid, and I get minus 43.8. Okay, so let's get this equation that I want. So I want one of this, and it's only in that one equation. So this first equation, I've got to keep it like it is because it gives me that, and it also gives me this in the correct position. Okay, so I need H2O2 as a reactant, and it has to have a 1 on it. So this one, I'm just gonna flip. All right, so let me switch colors again. Okay, so I'm gonna flip this one. So H2O2 is H2 plus O2, so that's gonna be a positive 191.2. So we'll mark that out. All right, so now this is where it needs to be. And then I need H2O liquid with a 2 coefficient on the product side. So this one, it's already on the product side, so I just need to multiply by 2. So 2H2O gas yields 2H2O liquid. That's gonna be a positive 3.8. Let's mark through there, and that is now where I need it to be. So now all that's left is I gotta make the other stuff cancel. So 2H2O gas and to to cancel. So I'm gonna go through this one by 2. 2H2 plus O2 yields 2H2O gas. So that's gonna be negative 241.8 times 2. Okay. And so now that cancels that. And let's see. Okay, so O2, 1 O2 there and 1 there. That's gonna cancel. And then on the product side, we have 2 H2s, and on the reactant side, 2 H2s. That 2 will cancel that one and that one. Okay. So now one thing to note in this, all right, is that one of the equations, right, we have canceled out everything, right? But still include its delta H in the when we add them all up. So however many equations that you start with, you're gonna add that many delta H's together, even if completely cancels out the way that this one did. Okay. So, let's get another again. Alright, so my delta H equation then is gonna be 177.4 plus 91.2 plus a negative 21.8 times 2 plus 43.8. So 177.4 plus 1.2 plus a negative 1.8 times 2 plus 40.8. So I'm getting negative 71.2 on that. Okay. So pretty straightforward. Um, these actually problems are usually the ones that whenever somebody sees that there's a Hess Law problem on an AP exam, it's like, "Yay." Okay, because this is one thing that once you get the hang of it, it's pretty easy to do. Um, so I've put another worksheet on the, um, on Otis, for practice, if you practice with that, and then there's this, brief quest, set of questions in there for you to practice with as well, on there. But basically, you just wanna jump in and do it because that's got your 4 rules, and just practicing with it is pretty much the key to being able to do Hess's Law problems. Okay, so I haven't looked at the gym board this morning. I did reopen, Quest. There were some people that, needed some more time with so just let me know if that's the case. Alright, let's get to a jam board. Okay, I'm back now. I guess I got a little click happy there with my thing. Okay, so let's go and let's see. Mm, okay, let's go here. We'll just do this here. Hmm, okay, or did anybody have any questions or anything? Let me just look. Check out the Jamboard here to see. Oh, yep, here we go. Okay, all right, so let's take a look at this. Um, oops, can I make that bigger? Molar heat capacity of the liquid. So it's giving me joules per mole degrees Celsius for the liquid and the gas and the melting and the vaporization. All right, so first off, let's get that out of those sentences and get it into something that's a little easier to work with. Okay, so that means, so here, if, all right, so this is my curve. And so the liquid, it's saying that for the liquid is 136, and this is in joules per mole degrees Celsius on there. So it's per mole, not per gram. And the gas is 81.6. That's joule per mole degree Celsius there for the gas. And the melting, so delta H of fusion is, oh, and that's the other thing, okay, is that this is in kilojoules, so 9.92 kilojoules per mole. And the vaporization, so delta H of vaporization is 30.8. Yeah, watch the units in this one because we got kilojoules on our delta H's and we have joules on our specific heats. It says the melting point is 5.5. Boiling point is 80.1. So that's 80.1. Molecular weight is 78 grams per mole. Okay. So the molecular weight, it's 78 grams per mole. And so so this one has 546 grams at 5.5. So it's starting, and it says it's a solid. So it's all solid. So it's going to be at that point right there on the curve. Into benzene vapor at 100. So we're stopping here. Let's make these points. So we're starting here, and we're going to stop somewhere up here at 100 degrees C. So we're starting at 5, right at the melting point on there. So you're going to have 1, 2, 3, 4 pieces to calculate for that one. So I'm pretty sure for this one, it's if somebody was confused about it or wasn't getting the right answer, that it's probably just getting all of those sentences into, like, putting it on the chart here so you know what's what. And then also the other thing, again, is being careful about, one, that we're using all of these values are per mole. So we're going to use that molar mass to find out how many moles we have on there, because each of these will use a mole. And then pay, they didn't, okay, this doesn't have what part of the problem is, if it wants it in joules or kilojoules, but whichever one it wants it in, just be sure to convert, your specific heats or the delta H's, whichever needs to be converted in there, because you've got different units, kilojoules and joules there. Okay. All right. If I didn't address the issue with this question, just let me know on that. How many calories are required to heat 18 grams of ice at -7 to 18 grams of liquid water? All right. So here, all right. So we are going to be starting somewhere down here at -7, because this is water. So that's at 0. We don't really need that, but that's at 100. And to water at 25 degrees Celsius. And so for here, right here, our specific heat is 4.18 joules per gram degrees Celsius. The solid was, we had that yesterday. Hang on, let's go back to the heating curve. Where did we put those values? I thought we had a heating curve where we wrote all those values yesterday. Maybe I put it on a different page. Oh, well, here, this table on that worksheet from yesterday has it. So solid is 2.02. Let's go back to our Jamboard. Okay, so C, 2.02 joules per gram degrees Celsius. And my delta H of fusion was 334 joules per gram. So 334 joules per gram that you would use on that. And then you would use that 1 calorie is equal to 4.18 joules to convert your final answer into calories, because it's asking for calories on there. So you would just have 3 calculations to do on that one. Okay. Okay, so it's given us specific heats. All right, so again, let's just pull this out, put it on our table here. All right, so we have solid. All right, so this one's slightly different, 2.09 joule per gram degrees Celsius, and then 4.18 joule per gram degrees Celsius. This one is 2.03 joule per gram degrees C. Then our delta H fusion is 334 joules per gram. And this one is delta H of vaporization. So 2260 joule per gram. Okay, so here, all right, we're going 74 grams. So we're starting at -20 minus 20, and then that's at 0. That's at 100. To liquid water at 70. So we're stopping here at 70 degrees. Okay. Wants it in kilojoules. All right, so here, so my Q then is going to be Q, so I'm going to heat the solid, and then Q to melt plus Q to heat the liquid. All right, so heating the solid, right, I'm going to go, and we'll just do this in general here, because it looks like the focus here is on our temperature changes, maybe. All right, and then this, so this will be 0 minus a minus 20, okay? And then plus the delta H of vaporization. So that's going to be mass times 334 plus, and then I go MC, and then it's going to be 70 minus 0. Okay, so I think that's the issue with this one, because the temperature change is, this is using the specific heat of the liquid, so heating the liquid, and so my liquid is starting at 0 and going up to 70 for this problem there. So I think that's this part right here was where the issue was on there. Okay. All right. We're all water. Okay, so here we're at. All right, so I'm at water at 21. So I'm somewhere around there, and converting it into liquid vapor. So that means I'm going to here, that's at 100 degrees. So we're going to use, so we'll need our 4.18 there. We'll need this one, the delta H of vaporization, and that one was, look at my chart again, 2260 joules per gram. 2260 joules per gram. And so I'll only need those two, because so my Q, I'm going to have MC, and then it's going to go 100, right? Because this is at 100 there. 100 minus 21, and then plus my delta H. So my delta H, and then times the mass on there, and then convert to kilojoules because it wants it in kilojoules. So that one's just going to have two values you're going to add together. All right. Let's see. Is that all? All right. Anybody else have any questions? Okay. All right. If there aren't any questions, I will see you guys tomorrow.